Now let's talk about graphing linear equations. There are three main techniques that we can use. The first one we've actually already seen. So one thing that you can always do with graphing is you can always go back to that plotting points method. And we did this back in section 1.1. So this method is going to work for really any kind of equation. For more complicated equations that are curves and things, you may need more points. But for lines, it's actually not bad. You just need at least 2 points to graph a line. So for plotting points, you can pick a value to plug in for either variable. Like for instance, pick x equals 1. Solve for the remaining variable. So if you pick x equals 1, you would solve for y, and that would give you 1 point. And then you're going to plot this point, and you're going to repeat the process. And you need at least 2 points to graph a line. Oftentimes, I like to do a third point just as a check. If you see 3 points in a straight line, then you're probably all set. My math lab will probably only let you graph 2, though. So it's just kind of just a little thing to note there. Now, the two new methods I want to talk about today, and I'm not going to go into detail with this in this video because we've already done it. So if you need to review this, go back to section 1.1 and just review the basics of graphing and plugging in values. The ones I'm going to focus on today are the intercepts method and graphing using slope and the y-intercept, so using the mx plus b form. So we'll do the intercepts method first. The intercepts method is actually very similar to plotting points. It's just that instead of picking any value you want to plug in, we're going to pick the zeros. So we want to find specifically the x-intercept and the y-intercept. So we're going to find the x-intercept by plugging in y equals 0 and solving. And then we're going to find the y-intercept by plugging in x equals 0 and solving. Then we'll graph these 2 points. As needed, you could always find additional points. So if you want to find that third point or extra points, you all can always do that. But if it says to use the intercepts, then those are the two that you really want to graph in my math lab. Otherwise, it will mark you wrong. The only exception is sometimes your x and y intercepts could be the same if they're both the origin, in which case you would then need another point to graph. But otherwise, usually this method works pretty well. So before we do the last one, let's try this method here first. So let's graph using the intercepts. So I'm going to go ahead, I'm going to find the x-intercept first. And to find the x-intercept, you always are going to plug in y equals 0. So I would have 4x minus 3 times 0 minus 6 equals 0. Now this piece is going to cancel. 4x minus 6 equals 0. And then I'm going to keep solving. Now I do get x equals 6/4, but I do want to simplify that, which is 3/2. If you have a hard time with this, you could also use your calculator and know that this is the value 1.5. So my x-intercept is actually 1.5, 0. And then I'm going to go ahead and find my y-intercept. So we plug in x equals 0 here. So 4 times 0 minus 3y minus 6 equals 0. I'm left with minus 3y minus 6 equals 0. I'm going to add that 6 to the other side, just doing regular solving now. And I'm going to divide by -3. And I have y equals -2. So my y-intercept, x value was 0, y value is -2. And these are 2 points. So for graphing a line, you need 2 points at minimum. So my y-intercept is 0, -2. My x-intercept is 1.5, 0. So I'm just going to estimate that. It'll be about right here. And then I'm going to go ahead and draw that line right through. All right. So there are your 2 points. There's our line going right through. You don't have to use different colors, of course. I just was doing that just to show you the 2 values. Remember that your x-intercept is where you cross that x-axis, and your y-intercept is where you cross or touch that y-axis. So you can see that's the point on the x-axis, that's the point on the y-axis. So you have those 2 specific points. Now you can always find extra points. So I'll just do one of those here just to kind of practice a little bit. So let's say you wanted to find an extra point. Then I could pick any value I want. So this goes back to just the plotting points method, like x equals 1. And I'm going to plug that value in. And I'm going to solve. 4 times 1 is 4, minus 3y minus 6 equals 0. Now 4 minus 6 is -2. So I have -3y minus 2 equals 0. I'm going to add the 2 to both sides. I'm running out of room here, so I'm just going to write the answer. So plus 2 would give me 2 on the right. And then I would divide by that -3, and I have y equals -2/3. So I get the point 1 common -2/3. And if I use that as my check, here's 1, and it does look like there's -2/3, right? It's going to be not quite at -1 here. So it looks pretty good. I'm right on that line. So I think I did a good job graphing here, and I didn't make any mistakes on my intercepts. A couple of things I want to note just with my math lab. One, if they do ask for a specific method for graphing, make sure you use it or they'll mark you wrong if you don't give the points that they ask for. So if it just says to graph or if it says plotting points, then you can do anything you want, any values you want to plug in. But if it says to use the intercepts, make sure you plot the intercepts. The only exception to that would be if both your intercepts were the same value of 0, 0, then you do need a second different point to plot in order to form that line. But otherwise, you should use your intercepts first. I will note too that my math lab does have a very difficult time plotting fractions. Sometimes they can plot things like halves or quarters, but you know, if you're using the plotting points method and you're getting kind of a weird value, I would suggest picking a different number to plug in because my math lab does tend to struggle with plotting fractions and marking the answers wrong, even though they may not be. So just something to watch out for as you're graphing in my math lab. Okay. Now, the next method, I'm going to do this example on the following page, is using the slope and y-intercept to graph. So this is great, particularly if you are in that y equals mx plus b form to start, because we can pick our slope and our y-intercept out right away. So if you're not in that form, you want to solve for y first. And then you can find your first point right away. You can find that y-intercept just right there. There's your b value. That's your y-intercept. You already have 1 point. Now your second point you use by counting with the slope. And you want to remember to use rise over run. So that numerator is that vertical change and that denominator is a horizontal change. And you're going to use that starting from the intercept to find your next point. And you can repeat that as needed. So let me show you how that works. And I think it'll make a little bit more sense. I have 2 examples here. All right, so here's the first one. Notice that we're in the correct form. Now we're using function notation here, but f is the same thing as y. So you're still in that y equals mx plus b form, or you can write f of x equals mx plus b. It doesn't matter. Both are interchangeable. So I can pick out my values, right? Here is my m, here is my b. So my m here is -3/2, and my b is going to be 2. Use a different color. So that b gives you the point 0b, which in this case is going to be 0, 2. So I already have my first point. That's my y-intercept. Okay. And I can go ahead and plot that right away. So 0, 2 is right here. So I can find 1 point without even plugging anything in. I already know one of my points. Now I use my slope to find the other point. And you want to remember the top part is the rise or the vertical change. And the bottom part is called the run or the horizontal change. And we're going to use those values to count. And the other thing you also need is the sign. So this happens to be negative. So remember, when you have a negative slope, your graph is going to be going down like this. So when we count the 3 and the 2, we're going to count in a downward direction to make a downward graph. So when you have a negative slope, you are either going to count down to the right, or if you're counting backwards, you would count up to the left. So in this case, if m equals -3/2, that means we're going to count down 3 and right 2. And we start at our intercept. So let's count. So I'm going to go down 3. So I start here. I go down 1, 2, 3. And I go right 2, 1, 2. And that's where I end up. Now I'm just using a light yellow just so you can see my counting, but you don't need that part. You just want the point. Now 2 points is enough, but you could do this over and over again. So I could start here now and go down 1, 2, 3, and go right 2, 1, 2. And so on. Now I mentioned you can also count. This is sort of the backwards direction. So let's say I'm counting to the right and I'm running out of spots. 1, 2, 3, 1, 2. 1, 2, 3, 1, 2. And I want to, maybe I want more points. Maybe I need like 10 points or something. And I run out of spots. Well, I can also count backwards. So instead of counting down to the right, going backwards, we're going up to the left. So you can go up 3, 1, 2, 3, left 2. Up 3, left 2. So that can just be helpful if you're, running out of room counting in one direction. You can work backwards. So the opposite of down and to the right is up to the left. And then you're just going to go ahead and connect those points. You obviously don't need this many points, but I just wanted to show you an example and how you could find more. Let's try another one. So here's our next one. And again, this is the same thing as having y equals mx plus b. So my m here is 2. And my b, just be careful, is a -5. So I know my y-intercept is 0b or 0, -5 here. So I can plot that one right away. Now my slope, if you don't have a denominator, you can always put 1 in, because this is the same thing as dividing by 1, right? Divided by 1 doesn't change anything. So here is my rise. Here is my run. Now remember that if you have a positive slope, your graph should go like this. So when you count, you're going to count up to the right. That's going to create that upward motion. Or if you're going backwards, you would count down to the left. Now we start with this point here, and then we're going to count. So in this case here, I'm going, because m is 2 over 1, I'm going to go up 2 and right 1 space. So I start here, I go up 2 and right 1. Again, up 2, right 1, up 2, right 1, up 2, right 1, and I can continue on. If I want some points on this side, just work backwards. Instead of going up to the right, you do the opposite, down to the left. So down 2, left 1, down 2, left 1, and you'll see that you have lots of nice points here that I can use to plot. Now remember with graphing too that there are points in between. So using this method doesn't give you every single point in the world. There are actually, you could plug in x equals, well, this one's kind of hard because we do have a lot of points, but let's say x equals 1/2, and you get that point in between. So you can still find all the values in between, but this is kind of a nice quick way to graph and quickly get a couple points so you can draw that line. Now, I do want to talk about a couple of exceptions here. So you have horizontal and vertical lines. These are more of exceptions. They're actually a lot easier to work with, so you don't need to go through usually the full process. So an equation of a horizontal line is always of the form y equals b, where b is the y-intercept. And remember, the slope of a horizontal line is 0. The equation of a vertical line is always of the form x equals a, where a is the x-intercept of the line, and the slope of a vertical line is undefined. So even if we're going to do some graphing on the next page, but even if you were finding an equation, let's say, you don't have to go through the whole process of the point slope form and everything. If you just remember that horizontal lines, if you know the equation is horizontal, it has to be y equals b, and b is just the y-intercept. If you have a vertical line, it has to be x equals a number, and a is the x-intercept. So if you have the basic information, then you can write that line right away. So for example, let's say I had something like write the equation of a vertical line through the point 2, 0, right? Well, if I see vertical line then I know it's going to be x equals a number. And I'm just looking at that x-intercept here. And that's my value. So x equals 2. That's it. So you can keep these in mind that they're going to be simpler and quicker and not to overthink them too much. So let's look at graphing them. So here we're going to graph the two equations on the same grid. So for x equals -2, again, this is always going to be a vertical line. And because it's -2, it's going to be through the point -2, 0. So that's your x-intercept. So if I find -2 here on the x-axis, I just draw that point, and I'm just going to draw a vertical line. Sorry, it's a little messy, right through it. Now on my math lab, you do need 2 points. So just click your point on the axis and then click any point right above or below it, and it'll draw that second point for you and connect them with the vertical line. For y equals 6, that's going to be your horizontal line. And it's through the point, let's see, here we're doing 6, so 0, 6. So I find 6 on my y-axis, and then I just draw a horizontal line right through it. Okay. And again, for my math lab, you will need 2 points. You can click a point on either side, and it will draw that line for you. Basically, what happens in these cases, they're a little bit interesting. So here you have the point 0, 6. And if you look at other points on this line, here it's 2, 6. Here it would be 5, 6. You're going to notice that the y value is always the same. So your y value is always 6 here. You're just going to run through all the x values. And then going the other way, this point is -2, 0. This point here is -2, -5. This point here is -2, -2. So you notice on the vertical lines, the x value always stays the same, and then it runs through all the y values instead. One last little note here. Sometimes they're not always in the final form. So you could see something like graph 4x plus 2 equals 10. And you're probably saying, well, that doesn't look like this form, but you want to notice that there's no y, it's just an x. So if it's just an x, it's going to be a vertical line. And what you can do in those problems, so if you see these, is you can just solve and then figure out what the simplified version is. And now you know that, hey, this is a vertical line. We don't see those too often. Usually when we're graphing, it's likely in one of these forms, or you're going to have a regular equation where you'd have an x and a y, right? If this is a 2y, that's different. But if you have an equation where it's only one variable and you're asked to graph, then you do want to clean that up first so that you know where to draw that intercept through. All right, so one last example here I want to talk about for applications, kind of going back to that idea of our scatter plot and our regression that we did at the very beginning of this section. So this example is from your text. It says the amount of carbon dioxide in the atmosphere measured in parts per million has been increasing as a result of the burning of oil and coal. The buildup of gases and particles traps heat and raises the planet's temperature. So the bar graph below shows the average atmospheric concentration of carbon dioxide and the average global temperature for 6 selected years. So they have 1960, 70, 80, 90, 2000, and then 2009. So here you have the carbon dioxide concentration in parts per million, and then here you have your global temperature. And then on the right, what they did is they displayed the data as a set of points in the rectangular system. So this is actually all the same data, it's just in 2 different kinds of graphs. So notice here, this point right here would be that 317, comma 57.04. This point here is that 326 column, comma 5706. So they just transferred the data over into a scatter plot instead. Now on the scatter plot, you do see that a line is drawn that passes through or near those 6 points. So we would assume that something like this could be that regression line, that line of best fit that, you can see it looks close to the data. And we want to write the slope intercept form of this equation using function notation. So look at the key idea, write the equation. Write the equation. So when we write the equation, we need a slope and we need a point. So those are two things that we need when we write equations. Doesn't matter which form you're in or how you're going to end up in the final answer. You need those two things to start. Now, regression lines can get very complicated. So usually we do actually use technology, or the formulas to do these out by hand are actually quite difficult. So when you're given in a regression line that's already done and you're asked to find the equation, what I want you to do is use the 2 points that that line directly goes through. So don't just pick any 2 points you want. Look at that regression line and use the 2 points that are given for the problem. And that's how you can find the correct equation of that particular line. So here I do have 2 points. I don't have a slope, but I can find it, right? I can use my formula y2 minus y1 over x2 minus x1. So here's 1 point and here's the other point. So my first y value is 57.99 and my second y value is 57.06. For my x values, here I have 385 and then here I have 326. All right, let me just find my notes. All right, so what we get on the top is 0.93. And then in the bottom, we get 59. And here you're not going to get an exact value, but I just rounded to 2 decimal places and got 0.02. Okay, so now we have our slope. Now here for the points, notice that I don't have the y-intercept, I just have 2 random points. So you can pick whichever one you want to use here. There's nothing really telling us to use 1 point or the other. So the point that your book used was that 326 point. So I'll stay in line with them. So I'm going to use this point here. And again, I don't have the y-intercept, so I have to use the y minus y1 equals m times x minus x1 formula. So if you need to, you can go all the way back to, what is it, the 3rd page of the notes. Right here when we were talking about the different ways you can write the equations. So I have y minus 57.06. My m is 0.02, x minus, let's see, 326. I'm going to simplify here. So I have y minus 57.06. I'm going to multiply through by that 0.02. And I get 6.52. And then I'm going to go ahead and add that 5706 to both sides. And I just use my calculator here. Okay. So here's our linear equation. They do want us to use function notation here. So that's the last change I'm going to make. Instead of using y, I'm going to replace this with f of x. Okay. So this is my final equation. And I didn't do anything new. So I use the same techniques I've already learned in the beginning of these videos for this section. When I see write an equation, that's what I'm going to do. I need my slope and I need my point. And here, when you're given the line for regression, use the 2 points that are given for the problem or the 2 points that that line goes through. And that will help you to write the equation of the line given. I will say in the real world, when you have lots and lots of points, if I have, let's say 100 points or 1,000 points, it's much more complicated to write that regression line. So usually we use technology, but with just a few points, we can write it a little bit easier, again, by using the 2 points that are given. All right, so the last thing says the pre-industrial concentration of atmospheric carbon dioxide was 280 parts per million. So I'm just going to make a note. And I'm going to just leave the units out for a second, just to make a note for myself here. So it says the United Nations Intergovernmental Panel on Climate Change predicts global temperatures will rise between 2 and 5 degrees Fahrenheit if carbon dioxide concentration doubles from the pre-industrial level. Okay, so we're saying that we're going to see a rise of 2% to, 2%, 2 degrees to 5 degrees if pre-industrial level doubles. Well, doubling means that I'm taking that 280 and I'm multiplying it by 2, right? So I would end up with 560 parts per million. So we're trying to say that if we actually hit 560 parts per million there, then we're looking at an increase in temperature of 2 degrees to 5 degrees. That's the prediction. Okay. Compared to the average global temperature of 57.99 degrees for 2009, how well does this function from part A model this prediction? Okay, so that's our question here. Compared to the average global temperature of 57.99 degrees Fahrenheit for 2009, so that was this year right here, right? We're at this point right here. How well does this function part A model this prediction? So what we're thinking about here, it's maybe a little bit hard to see, but the prediction involves us doubling that pre-industrial level. So we're really trying to figure out what's going to happen when our average carbon dioxide concentration is 560. So what we want to do here is plug that into our equation. So we're going to take our equation here, and we're going to evaluate it at 560, right? Because our X values are the average carbon dioxide concentration. So I want to see, well, what happens at 560? So I'm going to plug this right in. 0.02 times 560 plus 50.54. Let's see. We're going to get 11.2 plus 50.54, which is 61.74. And again, our Y value is degrees. So this is degrees Fahrenheit. So our equation here is predicting that when the carbon dioxide level is 560 parts per million for the concentration, that the global temperature on average is going to be 61.74 degrees. So how does this compare to the temperature now? Well, or in the problem. So I guess now is 2009, right? So in 2009, that temperature is 57.99. And then at 560 parts per million, we're predicting a temperature of 61.74 degrees Fahrenheit. So if I look at the change here, so this is about 58 degrees. This is about 62 degrees. This is a change of about 3 degrees Fahrenheit, right? Not exactly, but actually more like 4. Let's see. 58, 59, 60, 61. Yeah, almost 4. So maybe we'll say 4 degrees, better rounding. So a change of about 4 degrees Fahrenheit, which does match the prediction. They predicted that it was going to rise between 2 and 5 degrees Fahrenheit if that level doubles. And our equation is saying about 4 degrees, between 3 and 4 degrees is what we're seeing there. So it does look like that we are on track, or not we are on track, but their prediction is on track for how that temperature could change in the world.